So thanks for the introduction. We have a 3D object we want to reconstruct, and our acquisition trajectory is a circle around this object. So here is the view in the midplane, which is the plane containing the source trajectory. And so the nature of the truncation is the following. We have a detector whose extent is not large enough to measure the whole object. So only the red area is measured. And so this is the same truncation for all source points. So the area which is viewed by every source position is the red disk. So we suppose no axial truncation. So the area viewed by every source position in general is the red cylinder, so on the left figure. And finally, so in the midplane on the right, we can see that in the red disk, all the lines are measured because they intersect a source position. So we called this red disk the field of view, which is the set of points measured in every direction. So basically, we know all the line integral for the line crossing the field of view. And this is true only in the midplane. So here, we know that there is no exact reconstruction possible outside the midplane because the single orbit trajectory does not satisfy two sufficient conditions outside the midplane. And in the midplane, we know that there is no possible exact reconstruction outside of the field of view. Moreover, the well-known Feldkamp-Davis-Kress algorithm is not suitable here because of the transverse truncation of the cone beam projection. So the question is, how can we replace the FDK algorithm? So find another method that handles the truncation, and what region can we expect to reconstruct? So in the midplane, so for the reconstruction inside the field of view, we know two analytical methods that can handle truncation and perform a reconstruction in a part of the object. So they are the differentiated back projection, DBP, and the virtual fan beam method. So outside the midplane, the DBP was modified by Yu et al. 2006. However, the virtual fan beam method has not yet been modified to this context, and so this is the goal of our work. So I will now explain what is the virtual fan beam method. So first, I have to talk about a super short scan. So what is a super short scan? Basically, it is a trajectory which is not enough to measure the whole 2D object. So for instance, it means that there are lines which are not measured by this trajectory. So basically, for instance, this line, because it does not intersect the trajectory. And despite so this missing data, we can still perform exact reconstruction in a part of the object. So this is why. If we consider a point P, so if every line passing through P intersects the trajectory, and that the trajectory is composed of non-truncated projections, so that here the detector is large enough for every source position, then we can perform exact reconstruction on this point P. And so here, it gives us as a region of interest, well, the convex hull of the trajectory. So we can exactly reconstruct all the area in the convex hull of the trajectory. So you may have recognized 2D analogous version of three sufficient condition as those two conditions, so that every line through the point intersects the trajectory, and that we have a non-truncated projection. So here again, we need non-truncated projection. So how can we do with our problem with truncation? So the idea of the virtual fan beam method will be to devise a new virtual trajectory for which we have no truncation. So it means that for a virtual source point, we need to know all the ray integral for the ray starting from this point. If you remember, so in the field of view, we know all the line integral. And now from this line integral, we need to have the ray integral. And this, in fact, will be possible for all the points outside of the convex hull of the object. Basically, if you take a point outside the object for a given direction, so there are two rays, and at least one of the two rays will not intersect the object. So its integral will be 0, and we can attribute the line integral data to the other ray. So with this, so we can choose a virtual trajectory. So for instance, here we take the arc of circle at the border of the field of view and outside the object. Then we can rebind our truncated acquisition data into a non-truncated projection for this virtual setting. And finally, we can apply a super short scan reconstruction formula on this virtual trajectory. So this is the principle. Now let's see how the rebinding is performed. So how we go from our acquisition data to the virtual data. So we have those two trajectories. In blue, the acquisition trajectory, and in red, the virtual trajectory. And so for any point of the virtual trajectory, we need to get the ray, so all the ray of a given point, and we will take them from the acquisition trajectory. So for a given ray, it has a parameterization in the acquisition geometry, and those parameters, so the angle lambda, gamma, and the radius r, then they can be linked to some parameter phi and s, and this can be done for every circular trajectory with any radius. So basically, the same work can be done for the virtual geometry, and here we have our link between the acquisition data and the virtual data. So next, I present now the virtual fan beam formula that we apply in the midplane. So as we have just seen before, we have the rebinding from the acquisition geometry to the virtual geometry. Then there will be several steps in the virtual geometry which correspond to the step of the super short scan formula. So several steps. So this step is important because it is the one which requires no truncation. So this is the one we cannot perform in the acquisition geometry. So there are another step. Then we can go back once we have filtered our data in the acquisition geometry. And finally, we perform the fan beam back projection to obtain our reconstruction. Now, so let's go back to our 3D problem. So here is the geometry of acquisition of the cone beam projection. And now we will see how we adapt the virtual fan beam formula used in the midplane. So for the cone beam data. So we begin first by a weighting step. And then what we will do is to each row of the data of parameter V fixed, we will basically apply the midplane procedure. So first with the rebinding from the acquisition to the virtual geometry, then the different step in the virtual geometry. Then we go back to the acquisition geometry. And finally, we perform now a cone beam back projection formula to have our 3D reconstruction. So we performed a simulation first with a 3D Chaplogan phantom. So the reconstruction was a cube grid. And here we display 3 orthogonal slices, which are an axial slices, a sagittal slice, and a coronal slice. So we use an acquisition trajectory of radius 4 and virtual radius of 0.8. So we have displayed the virtual trajectory. So this is the arc of circle in the axial slice. And in the other slice, you can see that the midplane is the horizontal, the horizontal line. So with this virtual trajectory, the area that we can reconstruct is so the part of the object below the red, below the green dashed line. So for the axial slice, it is the part to the left of the red, the green dashed line for the sagittal slice, and it is the wall object for the coronal slice. So we compared our result with the FDK in case of non-truncated data. So here, for the axial slice, we can see that in the region of interest, we have a very similar and good result. If we move to the sagittal slice, we can see that for both FDK and our 3D virtual funding formula, we have an intensity drop away from the midplane, and that it is slightly different between FDK and our formula. And also there are some artifacts that are slightly different between the two formulas. And so this is basically the same for this slice, with an intensity drop away from the midplane and some small different artifacts. Next, we perform other simulation with head phantom, which is a more complicated phantom, so to have a more challenge. So again, we display three slices, an axial, a sagittal, and coronal slices. This time, we have an excision trajectory of radius 45 and a virtual trajectory of radius 9. So as before, we have displayed the virtual trajectory. So this time, we can reconstruct the part of the object above the green dashed line on the axial slice, the part of the object right to the green dashed line on the sagittal slice, and the wall coronal slice. So here in the midplane, we have again accurate reconstruction in the region of interest. We can see that the resolution seems different, and in fact, the result with our formula seems more smooth. It can be explained because we use several interpolation steps which add smoothing, which is not the case for the FDK. Then in the sagittal slice, now we can see a strong artifact, so both for the FDK and for our formula, but they seem stronger for our formula. So for instance, if you see the black circle, they are just on the right top and right bottom white part, which does not appear on the FDK reconstruction, and also the black part is extended a bit outside the black disk for our formula. So basically, we see a stronger artifact for our formula. And on this slice, it is even more clear. We see a big black strict artifact on our formula. And well, so this is stronger than the artifact obtained with the FDK. So to conclude, so we have modified the virtual fan beam formula to perform 3D reconstruction for a circular source trajectory with a transversely truncated cone beam projection. So in the midplane, we have applied the usual virtual fan beam formula. And outside the midplane, this formula was extended by applying the same treatment to every row for the parameter V fixed of the cone beam projection just after cone beam weighting step. So the midplane region of interest was extended actually. The formula is only exact in the midplane. Outside the midplane, it is only approximate. And so it was confirmed by the numerical result, because in the midplane, we have accurate reconstruction in the region of interest, while outside the midplane, we had only approximate reconstruction with visible artifact. So those artifacts were different between the FDK and our formula. They were stronger for our formula, but it can be explained since our formula used truncated data. So we had less data than the FDK. And so, well, this is the end of this presentation. Thank you for your attention. Do you have any question?
Yes, thank you for the nice presentation. I already see there's a question, please.
Hi, very nice talk. Just want to see, have you compared it with DBP, so differentiated back projection?
Not yet. In fact, the DBP result of you et al., they were applied to a slightly different configuration. Basically, if I want to show you, to explain, okay, going back. Yeah, so as you can see on the right, so the field of view, it is on one side of the object. And the DBP, they applied it to a different configuration where the field of view is at the center of the object, and there is a part at the left and at the right, which is not measured.
So you still can apply DBP?
Yeah, sure,
right?
sure.
So, yes.
But so what we wanted is first to have a very general formula before comparing it to DBP, because the next step of our work is to handle so this other configuration where the field of view is centered on the object with a truncation on both sides, so what we call bilateral truncation. So once this is done, we will of course compare it to DBP, but it has not yet.
Maybe a second question is that in the intersection between your object and the field of view, the intersection point, I see that your recon is pretty good. I was thinking that whether you would expect robustness there, like instability there, when do the recon. So when you do the recon, it's pretty stable in those points.
Mm-hmm.
And have you studied any noise impacts on those points on the reconstruction method, the VF, the virtual framing or virtual combing on your method?
So here we have not performed a noise study. We have done it in a paper to be submitted, so just for the 2D midplane, and basically the noise properties are similar to filtered back projection formula.
Okay.
So
yeah. Thank you very much.
I also have a question. Why do you go back to the acquisition geometry before doing the back projection?
Well, this is in fact for the 3D problem. Okay. In fact, in 2D, we could perform the fan beam back projection. We could perform the back projection in the virtual geometry, basically. But when we are in the 3D problem, the thing is, so for the 3D, what kind of filter data do we use? In fact, for each source position, we use the ray that passes through the point we want to reconstruct. And if we are not again into the acquisition geometry, we have no way to use the data we want. I mean, if we.
Yes, you have, because you can, of course, you don't have to do this, but you don't have to go back to the original geometry. You have your XY position of the ray because it's a 2D method, and then you know where it intersects the acquisition trajectory, and then you could basically deduce the direction of the, in the Z direction, the tilt angle of the ray and back project along this way.
in fact, the notion of virtual trajectory is only true in the midplane, and outside the midplane, we have no virtual trajectory.
I know, but you
yeah.
do the whole rebinning for all the V coordinates of your system, right? So you do the whole stuff independent for all the detector rows, what you show here.
Yes, there is only the last step, which will where V will be depending on the source, on the point to reconstruct. But in fact, if we stay in the virtual geometry, so we'll have data together. How to say?
I was just wondering, it's not too important.
Yeah,
we're complaining about spatial resolution losses, but I think they are not really a big issue, because typically you would not reconstruct in most flat detector situations at the highest spatial resolution. So it's not a problem if you do this little rebinning.
Yeah, I don't know. But another reason to go back to the acquisition trajectory is, well, the final goal of our work would be when we have some projection of the acquisition geometry which are not truncated, we want to treat them as the FDK. Basically, we want to stay as close as possible to the FDK. And well, this will need to be in the acquisition geometry.
I see. Are there any further questions? Not so. Let's thank the author again.